Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Keith Hawkins with us today. Hello, Keith. Keith is here. Keith,
Hello, how's everyone? Hope everyone's doing well. I'm Keith Hawkins. I'm at UT Austin. Oh, am I here?
you are here. You are here. So
Am I here?
just so people know, so Keith is actually in London at the moment, and I'm in Phoenix. So we have a little bit of a bandwidth lag, but we are going to make do with the best we got on this 22nd of May, 2023. And Keith, when you're not in London, what is your usual home base?
Yeah, I'm usually in the University of Texas in Austin, where it's nice and warm right now.
Nice and warm.
Nice and warm, nice and warm. But I'm actually in the UK visiting for conferences and visiting collaborators.
Very cool. Very cool. And I'm in Phoenix, and so like Austin, we get a little warm in the summer. The power switch has not been thrown yet, so we got about another week or so before the power switch gets thrown. Then we'll really be hot. But for now, it's very pleasant. So very cool. And Keith, what do you like to do for research?
Yeah, so I work on a field called galactic archaeology. I like to describe it as like I'm the Indiana Jones of the galaxy. So I try to piece together how the galaxy formed, how it assembled, how it evolved using all of the billions of stars that we can observe in the night sky. And unfortunately, that's still only about 1% of the galaxy, but it's still a large number of stars. So
Indeed.
I'm really interested in understanding the galaxy and particularly looking at the dynamics and motions and chemistry of stars.
Very cool. Very cool. And that is going to bring us to this very awesome APJ article. It is open access. We are in the open access era, people, so you can go grab a copy of this one for free. All of our past, present, and future will be free to access, so go grab one. The stars of the HETDEX survey: 1. Radial velocities and metal poor stars from low resolution stellar spectra. And Keith, take us away.
Wonderful. So this is a paper that I wrote a couple of years ago in 2021, and this is, I guess it's already been a couple of years. So indeed it does. And so this is about the stars of the HETDEX survey. So HETDEX is the Hobby Eberly Telescope Dark Energy Experiment.
Okay.
And that experiment is run out of the Hobby Eberly Telescope out in West Texas. Okay. It's a 9-meter class telescope, and their goal is to try to observe an unbiased, massively multiplexed survey in order to map out the locations and particularly the redshift distributions for Lyman alpha emitters across the universe.
Cool.
And so this is a huge project. It's a particularly galaxy-focused project, and there's been millions of dollars invested in this really awesome project. And so I want to thank my collaborators, who you can see listed there, but it's primarily the HETDEX collaboration that really kind of, really helped me with this work. Cool. Now, you might be thinking, what does dark energy have to do with stars?
I didn't go there.
And exactly, I mean, that's in the name. The Hobby Eberly Telescope Dark Energy Experiment, and yet it's stars. And so this has to do with something that I would say my father told me when I was a kid. Have you ever heard the term or the phrase, and one person's trash is another person's treasure?
Correct. I've heard that.
That's exactly what this paper is to me.
There you
go.
This
paper is me taking the trash of HETDEX. So HETDEX is looking for Lyman alpha emitters, but they have to observe through our galaxy. They have to observe all these stars by accident. And so their trash is my treasure. And that's what this paper really is all about in some sense.
Okay.
It's great. It's great. And so, so what this survey does is it is a massively multiplex survey. Oh, yes. Massively multiplex survey that is observing something like 34,000 spectra in an individual single image.
Wow, very cool.
So these are low resolution spectra, are of 750.
Okay.
But it's a massive number of them in one go.
Yeah.
And so what HETDEX is doing is they're basically pointing up the telescope. And if you go to figure 1, that will show you kind of where they're pointing in the galaxy, but they're pointing up in the galaxy. And they're basically doing a completely unbiased survey. They're not target selecting anything. Whatever falls into the fibers is what they get. They have millions and millions. They have 200 million spectra. Most of it is sky, of course.
Nice.
But some of it is Lyman alpha emitters, and many of it is actually stars. So you can see that in the image in figure 1 here, this is a galactic coordinates, where the galactic center is at 0 in L and 0 in B.
Yes.
And the black areas are the HETDEX fields. That is where HETDEX is looking for Lyman alpha emitters.
Okay.
Relative to the position of our galaxies. You can even see the small and large Magellanic clouds down there in the left corner of the image of our galaxies. The red is the cross match between the first data release of HETDEX, or the second internal data release of HETDEX, and Gaia.
Okay.
Now, one thing to point out automatically is that it doesn't quite follow the red should be inside the black because it's observing.
Right.
But there's an important point that I forgot to mention, which is that any time that the Hobby Eberly telescope is pointed anywhere on the sky for any type of science, Virus, which is the instrument doing HETDEX, unfortunately named Virus.
I was going to say
prior to the pandemic. So Virus, this instrument, is taking data no matter where the telescope is pointed. So even when you're not in the HETDEX field, you still get all of these very low resolution spectra.
Cool.
So this is a nice illustration of that. And so as HETDEX is going through its mission over the, it started, I think, in 2017, 2018, taking data, and it will be taking data for quite some time. I think it will be finishing up probably in the next 2 years or so, just under 2 years.
Okay.
And so it's about, a little more than 50% complete. Nice. And as they're taking data, they're basically collecting an enormous volume of low resolution spectra of stars. Enormous volume being like somewhere between we're expecting somewhere between 100,000 and 1 million spectra of stars.
Yikes, that's a lot.
Yeah, okay. It's a lot.
That's a lot of data.
It's an enormous volume of data. We're very lucky at Texas. We have the Texas Advanced Computing Center, or TAC for short. TAC actually is hosting the data and processing it for us. All the processing is being done there because the data volume is just so incredibly large.
Yeah, very nice. Very cool.
So in total, HETDEX will span something like 450 square degrees on the sky with a 1/4 fill factor roughly.
Okay.
And this paper talks only about 29.85 square degrees of that 450. So only 30% of the survey was complete at the time of this paper. Okay. And I'll talk about this at the end, but we're actually now really focusing on doing more work with the newest data releases, which is closer to 60 or 70% complete.
Nice. Okay.
So what we did in this particular paper was basically take all of the data that HETDEX had at that time and cross-match that against the Gaia catalog, because the Gaia catalog had point sources or stars. It had something like 1.5 or 1.8 billion stars at this point. Yeah. And when we did that cross match, I think we got something like almost 100,000 stars. I think we had something like 98. I think this particular paper deals with something like 120,000 spectra of something like 98,000 unique, what we think are unique stars between G of 10th magnitude and 22. So mostly focusing on the lower. Mostly focusing on the fainter stars. If you go to figure 2, that is representing the G-band distribution of our stars on the x-axis, and the signal to noise ratio in per pixel on the y-axis for all of the stars in the HETDEX survey. And this is for all 98,000. So we cover a wide range of magnitudes, 10 orders of magnitude, 10 magnitudes in total. And the signal to noise varies quite a lot. The dashed line is representing signal to noise of 5. Most of the stars are, of course, very low signal to noise. These are, by the way, I should say the virus instrument is only 24-minute exposures. So they're really rather short exposures in a particular region.
Right.
And what we're doing is, we have a fixed bundle of fibers. They're basically doing 8 minutes. They're dithering a little bit, doing another 8 minutes, dithering a little bit more, doing another 8 minutes. And that's where the 24 minutes roughly for every star comes from.
Okay, thank you.
And so what you're seeing here is the signal noise distribution, and the dashed line is signal noise 5. That's about where we say we have quality-ish spectra. Of course, obviously, a lot of this is low signal to noise because they're not really. This is not designed for stars, right? This is designed for galaxies.
Right, Lyman alpha.
Exactly, Lyman alpha. So table 1 represents the electronic machine readable table that is the entire catalog of HETDEX, cross-matched with Gaia. It's publicly accessible for everyone in case you're interested. We have the Gaia source IDs. These are the I believe the DR2 source IDs. Just beware, the DR2 source IDs are different than the DR3 source IDs. But this paper came out in DR2. And we also have the RA and DEC in Gaia RA and DEC as well, so that you can cross-match this rather easily with any survey. The Gaia G-band magnitude and some other information about the stars themselves.
Radial velocity.
We also have the radial velocity measurements. I'll talk a little bit more about that later, but with these really low resolution spectra, we can actually measure the radial velocities to pretty good precision. I was a bit surprised, actually. And for many of these stars, this Gaia will not measure the radial velocity for stars as faint as these. These are something like, for many of these stars, they're 20th magnitude, 18th, 19th magnitude. So this is the only radial velocity measurement that is available in the literature anywhere.
Cool. Nice.
So if anyone is interested in those, that's why we did it.
There was a big catalog there.
A huge catalog of radial velocities for faint targets, which is great. Okay, so if you go to figure 4, that is the figure that is the distribution of parallaxes and G-band magnitudes and colors. And so there we go. Here. And so you can see that the parallax distribution is such that it's peaked at fairly low parallaxes or relatively distant objects. There are even negative parallaxes, which means that these are extremely distant objects. They're actually not really negative. It's just
I was going to say, what?
Yeah, exactly. They're not actually negative. It's that Gaia can't measure, and it's consistent with 0, and with an uncertainty you end up getting as a negative parallax. So this just tells you that at really distant objects, the G-band magnitude peaks around 19 and a half magnitudes, and the color primarily peaks at just below 1, which for Gaia targets, this would be like your FG type stars. Although we do have going down to BPRPs of around 2 to 3, which is closer to your M dwarfs and starting to get closer to your L and T dwarfs. Since there is no selection, right? There's no selection here. This is in some sense an unbiased look at that particular region of the galaxy, that particular region of L and B space. Great. And so my favorite figure is figure 5, and this is the next figure in our story. As we're putting together, what we're trying to do is we're taking a massive survey, and we're trying to take that survey and use it for stars. So on the left panel, you have the Gaia color magnitude diagram of this HETDEX Gaia sample, called BPRP color on the x-axis, and absolute magnitude and G-band on the y. You can beautifully see the main sequence, the subgiant branch, the turn off, the subgiant branch, the red giant branch. In fact, you can even see the red clump and the red giant branch bump if you look closely enough. And then of course at the bottom left corner, you've got the white dwarfs.
More white dwarfies, indeed.
Exactly.
Indeed.
And so one of the things we did when we saw these was we want to see what does the spectra look like. So we basically did bins in absolute magnitude. The colors are indicated by the colors on the left side. And then we stacked the spectra, the HETDEX spectra, the R of 750, and then put them on the right side. So what you're seeing on the right side is the low-res R of 750 HETDEX stacked spectra for M dwarfs on the bottom. And then you go basically up, down the sequence. Or you can think about this as the top is the white dwarfs, very, very blue color.
Right.
And then the next down is OBAFGKM. So it's absolutely beautiful. When I saw this image for the first time, I started tearing up.
Yay! So I got two questions here.
Sure.
On the left, what are the vertical dash lines? What do they indicate?
Yes. So the vertical dash lines indicate the region where we were trying to measure radial velocities later on in the paper.
Okay. Good.
So those are just generally your FGK type stars in that band region. Okay. What is wonderful about this image is it looks like it's taken from a textbook. You can beautifully see how the spectra change as the stellar types change. The hottest stars only have the Balmer lines. The coolest stars, you start to see the TiO, titanium oxide molecular band heads appear. And we're in this beautiful region where we've got calcium H and K in the blue around 3,800 angstroms. We've got the carbon CHG band at around 4,300 angstroms. We've got the H beta feature around 4,800 angstroms. The magnesium triplet is even visible there. Those little bands around 5,100 angstrom, 5,180 angstroms.
Right here. Yeah.
And so beautifully, we can see all of these key features in stars, and we can see them beautifully.
So on the spectra, is each spectra for one star, or is this an average within, let's say, the orange band there?
Great. Yeah. So that is each spectrum on the right corresponds to a stacked median spectra on the colors on the left.
I'm with you. Very good.
And so this really tells you, or at least this tells me as spectroscopist, that the information content about a star, its temperature, its surface gravity, its metallicity, even probably its carbon abundances are embedded probably in those spectra. Nice. And it's probably high enough quality to do stellar parameter analysis. And why I think that's really interesting is because if you're a high-res stellar spectroscopist, you might be thinking, what am I going to do with R750? That's nothing. Turns out you could do quite a lot. And there's some nice theoretical work done by Wentz and Ting in 2017, Ting and Ricks. I think it's also an APJ paper or AAS Journal paper, where they predict how much information is embedded in low resolution spectra. And they predict that even at these resolutions, you should be able to measure not only temperature, surface gravity, and metallicity, which are the key atmospheric parameters, but also the abundance of carbon and abundances as well.
And if one is interested in galactic archaeology, that sounds like an interesting one to know.
Absolutely. So in order to flesh this out more, this paper goes into a little more detail. So in table 2, we cross-matched the HETDEX catalog against various other large spectroscopic surveys, Segway, Lemmost, and Apogee.
Yes.
And each one of these, what you're seeing in this table is the roughly the average G-band magnitude and dispersion of stars in that survey, and the number of stars that we have overlapping with those surveys. Okay. And the resolution as well. Now, why this is important is because the literature surveys like Apogee or Lemmost or Segway give us the opportunity to cross-validate some of the things we're about to do. Cool. So that's why we did this. And it's also important to note that of all of these surveys, higher resolution like Apogee or lower resolution like Segway and Lemmost, they're all average G-band magnitude is much brighter than what HETDEX is going. So HETDEX is one of the faintest large surveys of stars that has ever been conducted in terms of spectrum.
Nice. Nice. So we get some new information there. Very nice.
Indeed, indeed. So there were two final tests that we wanted to run with the HETDEX Spectra. And the point of this paper was more of a proof of concept that you can use the Spectra for something.
Yeah.
So there are two things that we did. The first thing we did was measure the radial velocities of the stars to see, are we at a resolution where we actually could measure decent radial velocity information?
Yes.
And the second thing we did was we didn't want to do the hardest thing, which was let's derive the stellar parameters of everything. We wanted to do the easy thing, which was ask a manifold learning algorithm, a machine learning algorithm like TSNE, or in this case, we use TSNE, to determine whether or not the information content is enough information content is in the spectrum to derive the stellar parameters or not.
Okay.
And so
those are good.
And so what the manifold learning algorithm does is it basically takes this, it's a dimensionality reduction code that basically takes all of the spectra and it represents those spectra on a two-dimensional plane, where spectra that look exactly alike are in the same region of that 2D plane, and spectra that look really different are in a different region of that 2D plane.
Okay.
And so all of that information is described in more detail in section 3.1, where we talk about the radial velocities. That is where we talk about how we do the radial velocities. We do a template. We do a template matching, and then we do a simple cross correlation, which is what's normally done for radial velocities. That's all covered in section 3. And then in section 3.1 and 3.2, we cover how TSNE goes about grouping spectra that look alike in the same region and grouping of spectra that look different in different regions of that 2D space. Now, I can talk about it, but I think that's a little bit more detailed than what we want to do for this audience, but I'm more than happy to cover that if there's time.
Let me ask one question. So this is a two-dimensional space, and so what are the names of those two dimensions?
That's a good question. So we don't really have names for them. They're just we just call it TSNE, the X dimension and the Y dimension. And the reason why we don't call them anything is because they are kind of 2D projections of a high dimensional data set. So they're not really physically meaningful, but they have some meaning in terms of grouping things that look alike in one region and grouping things that look different.
Okay, I'm with you. Thanks.
Yeah. So in section 3.2, if you that's the area where we really discuss how the algorithm works. Effectively, what it's doing is it's trying to reproject a high dimensional data set in a lower dimension, in this case 2 dimensions, without significant loss of information.
Okay.
So what it's going to do effectively is it's going to compute for every object, for every spectrum, it's going to compute a similarity score of how similar that object is to every other object in the data set.
Okay.
That's essentially what equation 1 is telling you.
Nice. Okay.
That's that P, J, I, that is the that is essentially the encoding the similarity score, if you will, of how every object in the data set, every object J in the data set compares to object I in the data set. Then what the code will do is it then takes all those objects, it puts them down on a 2-dimensional plane, and it recomputes a new similarity score. And it puts them down randomly, and then it moves them, all of those objects around until the similarity scores between this equation 2 is similar to the ones in equation 1.
Got it. I'm with you.
Right? So that's how it's embedding information. It's taking a many-dimensional space, computing what the similarity score is, and then it's going to that 2-dimensional space, starting out with a random projection, and then moving things around in that 2D space until the similarity matrix is similar between 1 and 2.
Got it. Very nice. I understand. Cool.
Awesome. All right, so that's the methods that we end up using. The results, the first major result is shown in figure 6.
Indeed.
So figure 6 represents the radial velocity, so results that we have. So what we do is we take we measure the radial velocities for all of the spectra in HETDEX. We basically take a low resolution synthetic grid, we match a template to the spectrum, and then we do a cross correlation. We measure the radial velocity. What you're seeing here on the y-axis is the radial velocity measured in a particular survey minus, or of HETDEX that we measure from the HETDEX spectrum, minus the survey, where on the left panel is the longitudinal sky survey segue, and on the right panel is the Lemos survey,
which has the biggest signal noise ratio. Yeah.
Exactly. And so you very nicely see the radial velocity. This is on the x-axis is the radial velocity of each of the surveys. You can see then that on the left panel, we measure the radial velocities with no significant trend in the difference. And we have an offset of something like 3 kilometers per second and a dispersion of 28 kilometers per second, which means we can measure radial velocities with these really low resolution spectra to something like within 28 kilometers per second relative to segue.
That's pretty cool.
We do the same thing with Lemos as a kind of a second check. We get a very similar value and sigma RV 27.7, but the delta is a little higher. It's like, you know, the offset between us and the Lemos radial velocity scale, something like 14 kilometers per second. Right. This is not surprising because there's a known offset between the segue one and the Lemos one, and that offset is roughly the difference between the two. So that's all understandable.
Cool.
So this figure is great. It tells us that we can measure radial velocities to within at least 30 kilometer per second precision with our HETDEX spectrum for all these very faint targets. Then figure 7, which is the next one down, we do a second validation check, which is there are some spectra of stars where it's the same star, but we got multiple spectra of that star. And so we can compare the radial velocity of each individual visit of the star, assuming that it's a single star, and see how well things compare. And so what you're seeing is the delta RV, the radial velocity of each individual visit minus the median radial velocity across all visits.
Okay.
Centered at 0, which is great. And dispersion is 19 kilometers per second, which means the internal precision of our radial velocities is something like 19 kilometers per second, which is fantastic.
Yep.
It does appear to be signal to noise dependent, which is what figure 8 is showing. We basically reproject that delta RV duplicate on the y-axis of that top panel as a function of signal to noise.
Yes.
And on the bottom is the dispersion, just telling you how well you're doing in terms of the radial velocity error as a function of signal noise. And what we're basically showing is that if you stay above signal noise of about 20, you have about 15, 16 kilometer per second precision, and then it blows up as you go down to 5. It blows up to about 30 kilometers per second.
Yeah. Still pretty good. Pretty good.
Yes, still pretty good. I did not expect to get this precise radial velocities, but this means that for really faint objects, right, G of 20 magnitude, we can derive radial velocities for you and derive at least some orbits for very faint objects in the outer halo, which is pretty awesome for a survey that was not designed for this.
Yeah, we've got to keep reminding ourselves, right? This was not designed for this.
No.
Very
All
good.
right, so then the figure 9 is our second test, our final test that we did, which was our TS&E map, which is what is this particular figure is trying to address. What is the information content of the spectra?
Yes.
Is it good enough to actually derive the stellar parameters or not?
Okay.
So what you're seeing here is a reprojection of the spectra onto 2 dimensions, where every point that's close together have spectra that look identical.
Okay. Yes.
And every point that's far away from that has a very different looking spectrum.
Okay.
Every gray point is a HETDEX spectrum, but since we also had data from segue and from Lemos, we actually color code every star that has segue spectra by circles, and every spectrum that has the most data, we color code by triangles, where we have the temperature on the top panel, surface gravity in the middle panel, and metallicity on the bottom panel. And you can beautifully see the TSNE map allows us to very easily separate the cool and the hot stars that's in the top panel. We can beautifully separate the dwarf stars, which are high low surface gravities, to the giant stars, which is that little finger of very low log G. And most importantly, we can even find the metal poor stars. So if you look at the bottom panel, it's color-coded by metallicity. The orangey colors are metal rich, the blue colors are metal poor, and the blue points all group up in a particular region that's boxed where all the metal poor stars are.
Okay.
So this allows us to find metal poor stars without doing any stellar parameter analysis at all. It's just a completely fast way of finding candidates that could be extremely metal poor, which for our science is really interesting because the most metal poor stars are the oldest. And they're archaeological records of what happened in the early universe. So that's why we want to find them.
First supernova, second supernova, that kind of stuff. One question on these. Make sure I'm interpreting correctly. I mean, the morphology of each of the blobs is the same. And so does each dot is in the same position in each figure? So in other words, this triangle right here, this is this triangle here, this is this triangle here. Is that true?
Correct.
Okay. So are metal poor stars are giants?
Largely, yes.
And somewhat hot? A little cool?
Yep.
A little cool.
They're, I would say they're probably like 55.
Yeah.
5,000 to 5,500 Kelvin. So not hot, but they're
not 3,000 either. Right.
No. And not all of them are, right? So some of them are giants and cool. You can see that little finger where their metallicies are below. I should mention metal poor means below -1. In this particular figure, we were highlighting stars below -1.8, below -2, just as to highlight the fact that we can find extremely low metallicity stars.
Yes, that's important. Very cool. I'm gonna zoom in on that a little bit. That will be of interest.
So anything in the metallicity panel, in the bottom panel, that has a black symbol around it, that black symbol indicates that it's below metallicities of -1.8.
0.
So they're kind of, you can see that they're not necessarily all in the same space, but they're largely grouped up in that.
The kind of where one would expect on some sort of a normal, whatever that means, chemical evolution.
Exactly. So what we did is we zoomed into that region, into that metal poor boxy region. That's figure 10.
Ooh, let's do a real zoom in as opposed to my artificial zoom in. Here we go. Very nice. Very nice. Okay. Wait till Keith catches up.
Yep. So in figure 10, what we're trying to do here is we basically take that black box and zoom really far in to see what the structure is. And what we're particularly interested in is looking at candidates. So again, similar as before, we've got our TSNE X and Y dimensions, which is effectively a measure of how similar objects are in their spectra. Then we've got color-coded by metallicity. So you can see that grouping of, this is that grouping of stars that are metal poor below -1 or so.
Yes.
And you can see that cluster of regions that's really zoomed in and a spectra that have metallicities below -1.8.
Nice.
The zoom in there is what you're seeing is each point has a HETDEX spectrum. The gray points are spectra that we don't have a measurement for at all. There's no other high resolution spectrum of it. But the colored points are ones where we do. So what we do is we take the red and the black, which are two spectra that are right next to each other in CMD space, or sorry, in right next to each other in the TSNE space.
Yes.
Which means their spectra should look identical. And because these spectra are extremely metal poor, we're expecting them to be. And so in fact, The red spectrum, or the red star there, is a candidate HETDEX metal pore star. We don't know what the metallicity is. No one has ever measured it.
Wow.
The black star that you see there is a star that we know has a metallicity of -2 from the SDSS survey from Spectra.
Okay, well.
And so we select basically a star that has a known metallicity. We select a known very low metallicity and select the neighboring star and see, does it look similar or not? And so figure 11, our last figure, is are the HETDEX spectra of that particular candidate.
Ooh, okay.
And the known metal pore star.
Okay. All righty. Flux versus wavelength. Wait for Keith to catch up.
Yep. So what you're seeing here is on the y-axis, you're seeing the roughly normalized flux of the spectra. This is called BMC flux, boosted median continuum flux. We don't actually know where the continuum is, so we have to do a boosted median continuum instead. That's why it's called BMC. And on the y-axis, you have the wavelength of light. The most important thing about this is the black line is the metallicity -2 spectrum. So it is a star that has a metallicity of -2 dex.
Yeah.
The red line is the metallicity, or sorry, is the spectrum of this candidate metallicity star where we don't know what the metallicity is because no one's
the red star on the previous one. So our
exactly.
Colors.
And
okay.
And the blue line is a segue spectrum that has a stellar parameters that are within 200 Kelvin of the black line, surface gravity within 0.2 dex of the black line, but its metallicity is -0.3. So it's a much more metal-rich star.
Yes.
So this figure is basically trying to illustrate the difference between a metal-rich star in blue, a bona fide metal-rich star in blue, a bona fide metal pore star in black, and our comparison candidate star in red. What's amazing about this is that the red and the black look almost identical.
Yeah.
So this red star is likely a star that has a metallicity of -2 or below, but no one has ever determined that before. We're the first people to determine that.
Yay!
So with this, we have a catalog of something like a few hundred extremely metal pore stars that we think are probably below -2 or -3.
Okay.
And we're using the HETDEX spectra as a starting point. And we're now in the process of looking at higher resolution versions of those spectra.
Hey, that sounds like a question to follow up on here in a bit. Very cool. Very nice.
Yeah.
I want to thank you.
And so that's where the project basically ends.
Yes. Cool. I want to thank you so much again for walking us through your very awesome HETDEX 1 survey article. Very nice. Thank you. And you touched on it a little bit.
Thank you very much.
Oh, yes. I kind of love the delay. It's like a little echo chamber or something. It's great. So you touched on it a little bit, and let me ask. So where do you think? So this paper was published in 2021. So this is HETDEX 1. And so where do you think we go? Let's say from now over the next, let's say 2 to 5 years. Is there going to be a HETDEX 2? Is there a HETDEX 3? We've had some new telescopes come up, so maybe JWST or Roman or something along those lines could be useful. And maybe there's some work to be doing on the stellar spectra that is being matched. So some theoretical work. So where do you think HETDEX goes over, let's say, the next couple of years on this non-Lyman alpha project?
Yeah. So this this paper actually was the pilot survey to an NSF grant that I wrote, and that NSF grant was accepted, awarded. And so now we have HETDEX money, or we have NSF money to continue our pursuit of low metallicity stars. What we're planning on doing is we've got some, I just hired a graduate student who's in her first year, Zoe Hackshaw. She will be doing follow-up spectra of higher resolution. We're doing R4000 spectra using the Virus W instrument and the LRS2, the low resolution spectrograph on the HET, to follow up some of these low resolution candidates and confirm them.
Cool. Yes.
So that's going to be the first thing that we're going to do in the future, and that hopefully we'll be able to publish in AAS journals probably in about a year or just under a year.
Go Zoe.
Then we're going to take with Zoe. Yeah, Zoe will be first author on that. Then we'll go one step further, and we'll actually derive stellar parameters and abundances, hopefully stellar parameters at the very least, but abundances as well for all of the HETDEX spectra. And the goal is to derive the unbiased metallicity distribution function of the halo.
Yes. Yes. Very nice.
Yes, and that'll be done with likely the pane or the Canon, which is a machine learning algorithm for dealing with spectrum. So we'll apply those and try to get the stellar parameters out. So that's going to be another paper that Zoe will write on actually the catalog of stellar parameters for that catalog of stars. That'll be the second paper. And the third paper in that series will actually be doing the metallicity distribution functions, accounting for the selection function, which is fairly simple.
Yeah.
And the hope is we'll actually measure whether the metallicity distribution function of the halo is metal rich or metal poor.
Cool. Very cool.
So 3 more papers to come, minimum. Zoe will probably be first author of all of them, but there's going to be 3 more to come.
Very cool. Well, I really look forward to seeing this topic advance over the next couple of years. So it'd be very exciting. All right, cool. So Keith, that will do. Thank you very much again. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.